Okay, welcome everybody to our UFS seminar. Did you want to say something, Yen, before I introduce Jim?
I have something to say.
Okay, go ahead.
Just a couple of housekeeping things before we get the webinar started. Hello, everyone. This is Bhavana from Office of Science and Technology Modeling Division. Welcome to the UFS webinar series. Today's webinar is going to be presented by Jim Kinter about the UFS Research to Operations project. We'll try to finish the presentation by around 3:45 and save the last 15 minutes for Q&A session. Because GoToWebinar does not give the option for attendees to view each other's questions, I'm going to be reading out the questions at the end of the presentation. And before we get started, I just wanted to quickly go over on how to get notifications for the webinar and other things related to that. So if you go to the UFS portal, which is currently being shown in the screen, it's called ufscommunity.org. And then if you scroll down the home page, you come to this section called Stay Connected. And to subscribe to announcements of the webinar, click on Subscribe to Announcements. And then if you want to see upcoming webinars, click on Upcoming Webinar page, and then it shows you the list of past webinars and the most recent webinar that's coming up. And if you want to view our library of webinars that we held earlier, click on the View Webinars on YouTube section, and then it takes you to this web page where you can see presentations from the previous webinars and the YouTube recordings associated with that. With that, I'd like to hand it over to Dorothy, who's going to introduce the presenter to us today.
Can I say a few words before Dorothy? Yes. Hi, this is Yan. If you look at the chat window, I post this link to this Google form where you can recommend the speakers using that link. We are really welcome everybody. If you know anybody who has done great work in all areas, covering all applications, all the subject areas, please feel free to submit the recommendations. Then we will consider it, then fill in the bi-weekly webinar schedule. Another thing I want to say is 2 weeks from now, we are not going to have webinars because we are having this so-called PI meeting is to review the funding opportunity from the OSTI office, which is conducted in combination with the UFS user workshop. So that's on July 30th, right after the workshops. So you are all welcome. You check on the workshop website. It's going to provide the link to the agenda for that PI meeting as well as the details. Everybody's welcome to attend. Thank you. Okay, I give to Dorothy. It's going to introduce the speakers.
Okay, great, thank you. So we welcome Dr. Jim Kinter from COLA, the Center for Ocean, Land, Atmosphere Studies at George Mason University. So Jim got his PhD from Princeton. He worked at NASA, Goddard Space Flight Center, and University of Maryland before going to George Mason University. So he's professor and chair in the department. So he's the director of COLA, but he's also the chair of the Atmospheric, Oceanic, and Earth Sciences of the College of Science at George Mason. He's a professor and also has a graduate student and teaches. I noticed online he's teaching 2 wonderful classes this fall: global warming, weather, climate, and society, as well as predictability and prediction of weather and climate concepts and phenomenology. So I want to register for both of those if I can. They're fantastic.
You're welcome.
So Jim has been with the UFS, I think, almost since the beginning. And last but not least, he's one of the 3 project leads for this newly launched UFS R2O project, which he's going to tell us about today. So thank you, Jim.
Oh, thank you, Dorothy.
All right, so I'm going to mute everyone and make Jim the presenter now. Take it away, Jim.
Okay, can you hear me and can you see my screen?
Yes, we can hear you.
Okay, great. So let me get this out of the way. All right, how's that? Is the view okay?
Yeah,
Right, well,
yes.
okay, great. Well, so like I said, thanks very much to Dorothy for that gracious introduction, and also to the organizers for providing the opportunity to give everyone a briefing on the Unified Forecast System Research to Operations project, which is quite a mouthful. As you can see on the screen now, I'm presenting this this talk, but it's really the work of the three project leads, Vijay, Tallapragada, and Jeff Whitaker, and myself. And even more importantly, you see a lot of logos sort of traipsing across the bottom of the slide. And that's a representation of just how broadly we've been able to involve people from the research and development community who are interested in thinking about how to do research within a more constrained environment of thinking about how that research can transition to operations. Okay, so now there we go. So first I wanted to just, I want to first apologize. This is not really a science talk, and I know we would all prefer probably to be having a science presentation in these webinar series, but we all felt it was important to get the message out that there is this R2O project, and to let everyone know what we're up to and what we're hoping to accomplish. So first I wanted to start with some background. So I think probably many of you who are listening to the webinar are familiar that NOAA has had a program called the Next Generation Global Prediction System, the NGGPS. It's been in place for several years. And as part of the NGGPS program, there has been an effort to develop a strategic implementation plan. Everybody calls the SIP. And the most recent instantiation of the SIP, which I'm showing on the screen, just excerpting here on the screen, is from fiscal 19 through 21, defines the unified forecast system and talks about what sorts of things we would like to be able to do with the unified forecast system. So as it says there in red, the UFS is a community-based coupled Earth system prediction system, which is comprehensive and end-to-end. Of course, comprehensive and end-to-end are in the eye of the beholder, but we're hoping over time to build the UFS to be fully comprehensive, and to be able to end-to-end means going from observations to forecasts. Importantly, it's not just a model, it's a prediction system, so it also includes data assimilation as well as diagnostics and evaluation, verification, validation. The applications that we're intending to use the UFS are spanning from local to global, and run from sub-hourly to seasonal predictions. And seasonal for these purposes means all the way out to 2 years lead time. The UFS is intended to support the weather enterprise, and capital W, capital E, meaning it's intended to be both accessible to and providing products and services to people who are doing research and development, as well as people who are making use of weather forecasts, either in the private sector or in government. And of course, it's intended that over time, UFS will become the primary source for NOAA's operational numerical weather prediction, numerical climate prediction, and other applications. UFS serves both research and development and operations, which means we do R&D both within NOAA and in the community that collaborates with NOAA, and also for operational prediction within the National Weather Service. Another bit of background is sort of an inspirational message which came from an external group, that's the UCAR Modeling Advisory Committee. This is an ad hoc committee formed by UCAR that evaluates modeling going on within NOAA, not just within the Weather Service, but NOAA writ large. And in the last report from the UMAC, in 2018, there was this recommendation that to accelerate innovations that can make their way into NOAA operations, and also to provide the scientific community with a credible tool for doing research. So this is both R2O, transitioning research into operations, and also O2R, providing operational tools to the scientific community. And as it says in red there, NOAA must be all in developing and deploying a unified community model with a unified collaborative strategy. So there's been quite a lot of work since this report more than 2 years ago, thinking about how to develop a unified system and a unified collaborative strategy. There's a UFS steering committee that meets weekly to discuss strategy for how we can collaborate better, how we can communicate better, how we can share code, how we can share data. And this is embedded within that framework. And as it says there in the second bullet, modeling and data assimilation within the NOAA labs and in the cooperative institutes needs to be integrated and collectively managed. And that's kind of where this R2O project gets its inspiration. We also have guidance coming from that steering committee. There's a document put out by the SC called the R2O document. And in there, it recommends that, it points out that existing research to operations practices and capabilities are unlikely to meet the requirements going forward, particularly as we start to think about a fully coupled Earth system model providing guidance for forecast products across a wide range of applications. And also the R2O document points out that maintaining product generation in the short term with longer term evolution to a truly unified system is really the goal, but it is a challenge. And we need to start thinking, and not only start, but continue thinking about how to do that. So this project, the Research to Operations project, which was conceived last year in 2019, is really in many ways a new way of doing business. We are carrying out, and as it says there, it's an experiment. We're carrying out research and development activities within a broad community in a very collaborative environment, but with constraints that are imposed by operational imperatives. So the idea is that rather than just asking what if questions or posing hypotheses that are purely theoretical, we think about research problems that are likely to have an impact in the near term on operational prediction. Another thing that's novel is that we have deep engagement by both National Weather Service and NOAA's Office of Oceanic and Atmospheric Research. They are coordinating funding and coordinating management of this project. We have people from both inside and outside NOAA who are interested, who are engaged, and who are willing participants in this project, and all have agreed to operate under a single management framework, which I'll describe in a couple of minutes. The proposal that we are operating under at the moment is a 2-year proposal, but it is within a 3 to 5 year vision. And so this is kind of distinct from the usual annual operating plan methodology, where we think about what's the most important set of things we can accomplish in the next year. So we're thinking 2 years out and also thinking 3 to 5 years out. We've already started thinking about how that vision impacts the sorts of work that we're doing now. And the idea is so that we can keep doing this and keep every year revising our plans at the 3 to 5 year time range, so that we always have a pipeline that's feeding from research to operations. So how did we conceive of what's in this proposal and how the R2O project should proceed? So first, we started looking at what are the forecaster priorities. And these were gathered from testbed feedback, from stakeholder interactions, in particular, the Weather Service Office of Science and Technology Integration has a group of science and operations officers that work within the weather forecast offices in operations, and they provide, a sort of a wish list of things that they consider to be priorities for forecasting. And you see the list there. Quantitative precipitation forecast is biased. We need to have better, we need to improve things on the structure of storms, on the environment that we see before convection onset, enhancing the way we predict clouds. And this is, has a lot of aviation applications, thinking about sealing and visibility, improving the inversion in planetary boundary layer, which we see from time to time and place to place, reducing winter cold bias in the lower troposphere. So this is a known problem with global numeric weather prediction models, and improving track forecasts of stronger hurricanes. So here we have the issue that the track forecast has improved greatly over the last several years, but for strong hurricanes, we still have limitations in terms of how well the track is forecast. We also have a number of things that are modeling issues that came from the modeling community more so than from the forecaster community. We know that the mid and upper tropospheric flow is biased. We know that our near surface temperature and precipitation is biased. The surface temperature biased, in different ways over ocean and over land, and the precipitation is typically biased towards low intensity precipitation rates. Convective initiation is a problem in the model. We don't necessarily do as good a job as we should, at least in the global model, on convective inhibition. Zonal flow is biased, so that our hurricane track forecasts after day 5 are usually off, and we see a rapid growth in track forecast error at that lead time. And then as we look at the subseasonal forecast time range going out to weeks 3 and 4, where we see a sharp diminution of the forecast accuracy in most of the metrics we look at. So we're starting to look at research opportunities for doing a better job of exploiting predictability that may be present in the subseasonal time frame that we haven't been able to harvest in our operational models. So looking particularly at Madden-Julian oscillation as a source of predictability for the subseasonal time range. And so the models need to do a better job of predicting MJO intensity propagation and remote teleconnections from the tropics into the extratropics. We also know that there's quite a lot of potential for improving predictions if we get the feedbacks between the land surface and the atmosphere right. And also there is some work to show that interactions between the troposphere and the stratosphere have an impact on this subseasonal time range. We also, in addition to thinking about forecaster issues and modeling issues, we wanted to also think about what are the basic science problems. And so we know that for more than a couple of decades, coupled ocean atmosphere models have had a bias. And you know what those biases are, things like the double ITCZ, where we see 2 intense precipitation zones in the tropics when in principle there should only be 1. We need to do a better job of representing some of the key modes of variability like El Nino, and I already mentioned the Madden-Julian oscillation. We need to do a better job of data assimilation, so finding optimal combinations of Earth system observations and model forecasts. And for that, we really need to invest heavily in advancing our data assimilation systems, and particularly looking at how we can exploit the fact that we're using a coupled Earth system model for forecasts. Can we then use the observations from some of the other components, say ocean observations or land surface observations, to influence the initial states for the atmosphere? Same thing with sea ice, same thing with aerosols. Can we assimilate information from those to do a better job of initializing the Earth system model? Another science problem is convection allowing ensemble forecast capability. This is kind of a holy grail for the short range forecast. And we have quite a number of things that are running in operations now, and quite a number of promising research directions. So we want to bring those together. We want to improve initialization at all scales, from convective to global. And this is not only my third bullet there, looking at advanced data assimilation, but also thinking about how we can do a better job of pre-processing and thinking about our observational database. And finally, we're running ensembles of forecasts. So we have ample opportunity now to quantify model uncertainty. The question is, can we start to think about that in terms of uncertainty at the model component interfaces, fluxes between the ocean and atmosphere, between the land surface and the atmosphere, between the sea ice and the ocean, or the sea ice and the atmosphere? So that's really where we want to focus as we're going forward. For this project, we're employing a broad range of technical approaches. First and foremost is reusing code. So we are working very hard to coordinate development of shared modeling and data assimilation infrastructures across the whole project, and including both people inside NOAA and university partners. And you see here a list of several items that we're seeing as reusable software components. The one at the very top of the list is JEDI, the data assimilation system that's being developed at the Joint Center for Satellite Data Assimilation. We also have a number of software infrastructure capabilities for coupling model components. At the sort of the low level, we're looking at Earth System Modeling Framework, the National Unified Operational Prediction capability, which is a multi-agency development activity. Actually, both ESMF and NUOPSI are multi-agency development activities. The National Environmental Modeling System, and CMAPs, as these are mediators that take into account data that's flowing from one component model to another. We're also in the process of bringing online the community physics package. So this is providing us with interoperable atmospheric physics, physical parameterizations of subgrid scale physical processes. So we want to be able to use those both in global models and in regional short-range weather models. We're developing community data models that are going to make it possible to run the coupled system with constraints from observations on one or another of the components in the system. We are employing quite modern code management policies. These are developed by the whole UFS community, where we have repositories which are GitHub and Gitflow based. We also are working towards a community workflow, or I should probably have had an S there, community workflows, because we acknowledge that there's probably no single workflow to rule them all, but there will be a limited number of workflows with reusable components. So part of our project is to identify what those reusable components are in workflows and think that through. And finally, and very importantly, we're coordinating the development of our forecast verification tools. So we're building extensions to Met Plus so it can work with Earth system model output as well as just the atmospheric model output. And thinking through, how we're going to take advantage of these tools to do a better job of verifying models of the full Earth system. There's increased attention to documentation and user support. We are, leveraging work that's going on within the UFS Communications and Outreach Working Group. We are developing supporting databases, verification validation framework, which I already mentioned. And of course, we are coordinating with EMC, Environmental Modeling Center operations, to streamline and accelerate the transition from all the research that's going on in our project to operations. We have some initial targets, so operational models, the global forecast model, the global ensemble forecast system, and the hurricane system, which are getting up into these double-digit versions. These are the targets, and I'll show you a chart where the timeline is for those things coming online. We have two other things to mention within our technical approaches. We have a benchmarking strategy for both the global model for medium range weather and subseasonal to seasonal prediction, and a benchmarking strategy for the convective allowing model that will be providing short range weather forecasting. So in both of these cases, we have metrics which were developed in community workshops in the past, and this is going back a couple of years ago where we had a whole community workshop thinking about what the metrics are, and also thinking about known issues regarding either science and modeling issues or forecaster priorities. Thinking, for example, with convective allowing model, the optimal spread skill relationship to take best advantage of our ensembles, but also minimizing model biases. So the project is it's quite a large project. It's involving, as you saw with the list of logos on the first slide, a very large number of organizations, and I have a couple of metrics about that in a minute. So we've organized the project into two layers. One is the layer that we're calling the application teams. So we have one application team which is working with the global modeling system, and that's for medium range weather, or some people have been calling it Mr. Weather, and the subseasonal to seasonal prediction, or S2S. And then the other application team is working with the convective allowing model to produce short range forecasts of severe weather, hurricanes, and so on. And then supporting both of those application teams, we have a cross-cutting infrastructure team, which is providing software and infrastructure as well as validation and verification tools to support both of the application teams. Excuse me. Within each of those teams, we have a number of sub-projects that are where the work is actually getting done at a technical level. We have worked very hard to optimize our pathways of communication so we can coordinate and collaborate as best we know how across the sub-projects and across the teams, because as we've recognized, there's quite a lot of dependencies between the global and the regional modeling, as well as dependencies across different aspects of the Earth system models that we're developing. We are expecting to leverage NOAA cloud computing and projects that are funded by RFPs that have been issued by both Weather Service and OAR. And as it says there at the last bullet there, you know, we're working very hard to maximize communication. That runs a little bit counter to what many people would prefer. A lot of people would like to get marching orders and go off and do what they need to do and report out at some later date. But we understand that because of the size and complexity of this project, we need a lot of communication. So we have purposely made people have roles in multiple different sub-projects. We have established a schedule for lots of meetings. And some people are already worrying about how many meetings we have, but I think it's actually a reasonable balance between enough meetings to keep everybody informed and allowing enough time outside of meetings to get work done. We are building a capability to collaborate using available team tools, software that's being evaluated right now. And we are coordinating very closely with both the program offices in Weather Service, which is OSTI, and in OAR, which is the Weather Prediction Office. So this is the org chart for the project. And what you see at the top in red is the three project leads, Jeff and Vijay and myself. And I must say, I'm very pleased to be included in this group. Jeff and Vijay and I have been working very closely for the last 6 months now, working to get this project off the ground, and it's just been a great pleasure working with both of them. Also, we're working very closely with, as I mentioned, the project office, the program offices at Weather Service and OAR, and we brought on a team of project engineers. Farida has been really working. It seems like she doesn't sleep, working night and day to get us up and running, building all the tools and you know, management resources that we might need. We're also getting support from Stelios and from Kumar, looking at helping us build the different parts of the project and making sure everybody is communicating well. These are our two application teams in blue in the middle layer here, the Mr. Weather and subseasonal to seasonal application on the left. And the one in the middle are our short range weather, convective allowing modeling activity, and then our cross-cutting infrastructure team on the right. The people's names you see in yellow in all of these boxes are our points of contact for the overall project. So anytime we need to reach into the application teams or into the sub-projects to get information, those are our first phone calls. I guess that's kind of 20th century thinking. Those are our first emails, our first Slack channel requests, whatever. And then at the working level, you see all the orange boxes are sub-projects. So we're doing a sub-project on data assimilation, reforecast, reanalysis, and reforecast. We're doing a sub-project on coupled model development. There's a sub-project on physics, which is primarily atmospheric, subgrid scale physical parameterizations, and a sub-project on atmospheric composition to start bringing aerosols and atmospheric composition into the Earth system framework. In our short-range weather portion, we have 4 sub-projects. One, the three-dimensional real-time mesoscale analysis project, the hurricane forecast project, the rapid refresh forecasting system, and Warn-On forecast. Warn-On forecast is you know, in-kind contributions. And finally, our cross-cutting infrastructure team has 2 sub-projects, one on modeling infrastructure and the other on a verification and post-processing infrastructure. So we have a number of ambitious goals for this project. First, of course, we want to develop a number of modeling innovations, and we have a fairly long list of these innovations that are targeting for operational codes that are anticipated to be going into operations over the next couple of years. In addition to that, so that's our sort of our R2O piece, but also there's the O2R piece of the project, which is broadening access to all of these tools, the codes, the documentation, the data sets, to the entire research community. We are also hoping to make sure that the best available scientific understanding and an evidence-based decision-making process is in place to advance the models and help us reach our overarching goal, which is to bring the U.S. back into the front as one of the leading nations in producing accurate and useful weather forecasts, weather and climate and other application forecasts. Fourth, we want to accelerate development of the models in order to improve forecast efficiency, forecast skill, and forecast utility. So that's really the trifecta of what we're trying to do with forecasts. We want to advance our global modeling capability as well as our convective allowing modeling capability. So we're hitting both ends of the spatial spectrum, spatial scale spectrum. And again, taking into account forecaster priorities, scientific priorities, and modeling priorities in both of these areas. I mentioned that we have this cross-cutting infrastructure team is providing support. This is very important because we have, as part of our goal for the project, is to help the Weather Service simplify the production suite of models and tools that are run in order to provide guidance for weather forecasters, climate outlooks, and so on. And so because it's such a large and complex set of applications, it's very important to make sure that we have as much shared software as possible across the applications, reusing solutions, reusing tools, and reducing duplication of both code and programmer effort. And secondly, the CCI team is facilitating engagement of community partners. So this is by providing copious documentation, providing tutorials and workshops, providing code and data repositories within the context of the System Architecture and Infrastructure Working Group, and of course supporting regression testing, which is fundamental at EMC and is kind of a new thing for people in the university community to be thinking about. And then finally, supporting both users and people who are contributing code to the Earth system modeling capability. Wanted to also emphasize this point that the cross-cutting infrastructure actually has a role in all parts of the research and development and operational workflows. So there's infrastructure for doing pre-processing of input data. There's a huge infrastructure development being spearheaded by JCSDA on data assimilation. We have model components and coupling infrastructure. We have ensemble post-processing, as well as the verification, validation, and diagnostics that I mentioned earlier. So we had our kickoff meeting last week on Thursday and Friday, and I must say I was really very impressed. We had at the high water mark, we had over 200 people who were participating in the kickoff meeting. I think it was a very successful exchange of information and setting up for a project that's going to do very well. We had excellent discussions of what our goals are, both for the project as a whole and within each sub-project. What tasks are needed, who's going to be doing what, the inter-project dependencies, because as you saw from the org chart, it's quite a complicated program that we have in mind. What the experiments are, the numerical experiments that are planned to try to address the hypothesis testing that's necessary. And finally, computing requirements. And it's that last one which is really going to have to get a lot of attention as we go forward, because the computing requirement for this project is truly massive. But I'm quite pleased, quite optimistic. We're off and running, and I think the project is already doing great. So I mentioned I was going to show a timeline. What you see on this chart is time running from left to right, and here we are at the beginning of the project here. And we just had our kickoff meeting, as I mentioned, just a couple of days ago. So what you see on this chart is a number of horizontal color codes. each one of these colors on the left represents an application which is running currently in operations at the National Weather Service. So it's just a huge number of different applications. And you can see from the names of these applications that there's considerable redundancy in what they're doing. In some cases, these are to form ensembles, sort of ensembles of convenience, because these models were already running. So now we run them in ensemble mode. But also there's just some things that could be done in a more efficient way. So if you now look at the right side of the diagram, you see a significantly reduced number of colors, which represents consolidation from the left side to the right side of all of these applications to a single global application, that's the green at the top, a single mesoscale application, that's the dark blue in the middle. And really, this R2O project is focusing on those two substantial transitions. The green vertical line here is the beginning of our project. The red vertical line is the end of the funded part of our project. But as I mentioned, that's just the 2 years of what we have proposed, of the proposed work that's already been documented. And then out here is our 3 to 5 year time frame as we're thinking about what the vision is for where we want to be. So we want to be at the end of this 5 year period, we want to be in this state where we have a much reduced number of applications, which are providing a much broader range of capabilities. If we zoom in on just the global modeling apps for this, you see GFS version 16 and GEFS version 13 and version 17 of the global model. Oh, and I forgot to mention this black hole here in the middle is the moratorium period when the Weather Service is transitioning their operational high performance computing system from what's currently in place to what will be in place. So there's a 1 year period when no codes may transition into operations. And here I've just made this sort of blue stripes here, but here you can see this transition from lots of, I think we have 8 or 9 different global applications on the left, and a single global application and a single seasonal application on the right. Similarly for our short range weather with the convective allowing models, again, you see a number of different applications on the left, all transitioning to just 2, the hurricane and the short range forecast. So here are the outcomes we're anticipating, or we're hoping for in the first 2 years of this project. One is a fully coupled global ensemble prediction system with active components for the land surface, for the ocean, for the sea ice, for the atmosphere, and for the aerosols, including coupled data assimilation. And all of this will be ready for pre-operational testing and suitable for community research use. So the development that's going to go into getting us to this stage is addressing all of the science priorities I mentioned earlier, and we hope leading to improvements in the forecast priority areas that the forecasters have identified. It includes a reanalysis and reforecast capability in order to calibrate and reduce and correct biases that we find, and that should be in production by the 3rd year. We anticipate public releases of a coupled medium range weather application, a coupled subseasonal to seasonal application, and the public release of JEDI, all within the next 2 years. We also are projecting a regional rapid refresh capability with a 1 hour refresh cadence in an ensemble mode for convective allowing scales, and that should be ready for pre-operational testing at the end of this 2 year period, including, again, for community research use, a public release of the regional rapid refresh forecast system. And as we saw in this earlier diagram, or the last couple of diagrams, we're going to be sunsetting existing mesoscale prediction systems and transitioning to a single capability. If we look out longer term at the vision for 3 to 5 year, and these are really just highlights, we are anticipating a strongly coupled data assimilation capability for the global model. Strongly coupled in this sense means making full utilization of observations in each component to assimilate data into the other components. So for example, I mentioned ocean observations being used in the atmospheric data assimilation, all of this within an Earth system modeling framework. We anticipate having JEDI available to initialize all forecast systems from convective allowing up to the global scales. We will have the next generation moist physics suite for the atmosphere. unified for both convective allowing all the way up to global scales. We will have inline air quality capability for the United States, aerosol feedbacks on the medium range weather and S2S prediction. There will be a warn-on forecast capability running for the Storm Prediction Center's hazardous weather test bed event, as well as for Weather Prediction Center's prediction of significant events like flash floods. We'll have a hurricane analysis and forecast system everybody calls the HAFs, with moving nests for multiple storms. We will have the beginnings of a space weather application. And of course, important to the university community, we will have research publications in high impact peer reviewed journals. I think this is my last slide. The most daunting and challenging aspect of this, to me, I think all the people who are involved have great intentions of working together, and the collaborations have been going very well so far. So my big concern is the computing. What you can see on this chart is what we anticipate in terms of requirements for the medium range weather S2S application team, for the short range weather convective allowing modeling team, and for the cross-cutting infrastructure. And it's primarily the two application teams that have the big requirements. And you can see, and this is all just for the first year of this project. We're anticipating in excess of 750 million core hours of computing requirement just on NOAA R&D high performance computing platforms alone. We're hoping to augment that with, and I think these are conservative numbers. I think we're hoping to augment that with high performance computing that we get from non-NOAA sources, primarily large installations funded by the National Science Foundation and the Department of Energy, which of course are competitive. So we have to submit proposals and go through the review process to see if we can get that. And then finally, we're looking to the NOAA cloud to at least start getting codes ported over to the cloud and get the beginnings of cloud-based production computing. By year 2, of course, these numbers on the right for cloud computing we would hope substantially increase as we gain experience and capability to be able to use the cloud effectively, so that we would see big increases in these numbers and possibly taking some of the load off of NOAA's R&D HPC. As I note down here at the bottom, these numbers, this is actually no longer true. This is more like a half, I think, or maybe more than a half of what's the totality of current NOAA R&D HPC resources. So it's a big ask to be able to try to get this type of computing capability. And then finally, like I mentioned, I think that competitive allocations on NSF and DOE, Stampede 2 is one example, a system running at University of Texas. I think it's possible to get allocations of a few tens of millions of core hours in competitive allocations like that. So I'll be happy to take questions, and I guess Bhavana, you're going to, or Jan, somebody's going to help me with that, because I can't actually see the questions as they're coming in.
Right. So I can get started reading out the question. The first one is more of a comment from Daniel Menendez. He says, I'm surprised that hurricane intensity did not bubble up in the priorities from the field.
So that was just it was not meant to be an exhaustive list. It's definitely hurricane intensity is one of the things that's very high on everybody's list. Particularly as we see hurricanes about to make landfall, that's where we see the biggest problem in forecast skill, the hurricane intensity just before landfall. So yes, it's definitely something we're going to be looking at. My list was not meant to be exhaustive. I could have added, half a dozen additional priority items that came from the forecasters on all of those, both for hurricane and for severe weather and for global weather. All of them have more than just the ones I listed.
The next one is from Kiran Alapati. He says, I'm the developer of the multi-scale Kian-Fritsch MSKF CP scheme available in WRF. Right now, NCAR is taking lead to modify my MSKF scheme, meeting CCPP's requirement as part of the MPAS model. This is a scale-aware CP scheme. So would you be interested in testing it on your framework once my scheme is tested in MPAS and released?
Well, so I don't think that's addressed to me. That's addressed to the project, and I think the answer to that is yes. We're very keenly interested in exploring options for the subgrid physics. Whether a test if that system is at a level of maturity as the questioner describes, then it's something we could test right away. My guess is that it's probably going to be something that'll be in year 2 or beyond. But I mean, that's the whole point of this project, is to be able to entrain research developments, particularly if they've been cast in the framework, for example, of CCPP. The whole point of adopting CCPP within the R2O framework is that we can actually do what was just described. So the short answer is yes. Longer answer is not sure when exactly that can happen, but hopefully it could happen within the first 2 years.
Okay. Next question is from Evan Kalina. Says, Jim talked quite a bit about the level of collaboration through NOAA, NCAR, and academia in this project. I was wondering if there was also international collaborations taking place. Are other modeling centers like UKMet or ECMWF participating or advising?
So the answer is no, not within the context of this project. The R2O project is funded specifically with U.S. investigators. I have all the logos up on the screen. You don't see any international logos. But having said that, of course, all of us have our connections to international partners. And in terms of advice or in terms of reaching out, I don't see any barriers to us doing that. But it's not formally part of the project.
Next question is from Israel Jirak. He asks, what is the expected or anticipated role of NOAA testbeds in the UFS R2O projects?
Okay, that's a great question. I'm not really all that qualified to answer it. There was one place in my slide where I mentioned that we are anticipating working closely with the hazardous weather testbed. And in particular, we have OU is here on our list, as well as the Storm Prediction Center is involved. So there is an opportunity for testbeds to participate, but we only have a couple of testbeds that are formally included in the project at this point. I think if we hear from people who are interested in participating, that would be something we would definitely want to look into.
Okay. The next one is a comment from Vijay Tallapragada. I think he's answering one of the previous questions.
Great.
He says hurricane forecast goals, HFIB, are handled through 8 sub-projects, which will become in-kind for UFS R2O.
Right, so he's referring to the hurricane supplemental projects.
Okay.
Right.
Next question is from Srinivas Murthy. He says, I saw on one slide SFSV1, but there was already a SFSV1 in 2000 implemented by Kanamitsu Mingji et al.
Okay. You're talking about down here in the lower right-hand corner. Yeah, so these names come to us from EMC. So I can't really comment on why that one's not named VX, where X is greater than 1. So the intent is that this will be a new coupled seasonal forecast capability using the FE3 dynamical core atmosphere coupled to 5 other active components: land surface, sea ice, ocean aerosols, and ocean surface waves. So that's what's inside SFSV1. It will be a successor to CFSV2. And I'm not entirely sure what Murthy is questioning there, but anyway.
Okay. Next one is from Young Joon Kim. He asks if RRFS does not produce results that match the existing systems based on multi-model ensembles, it might not be transitioned as planned according to the evidence-based decision.
That sounds like a statement, not a question. I'll just say yes, that's true. There is a set of metrics that are predefined and a set of benchmarks that are required for the models to meet or exceed in order to transition operations. So like I said, we're doing this research within that constraint, within that operational constraint that you can't implement something that doesn't do better than what it's aiming to replace.
Okay, so apparently I probably didn't read the question right. Yang is correcting me, saying I should ask the way it was asked. It wasn't a statement, so I'm going to repeat it again. If RRFS does not produce results that match the existing systems based on multi-model ensembles, it might not be transitioned as planned according to the, in quotes, evidence-based decision, question mark.
Right, it won't.
Okay. Next one is from Ahmed Khalifa. Any facility to scale down into smaller regional models? Question mark.
Yeah, so what's on the screen right now, these are all these blue guys are regional models, and they're all running at quite high resolutions. I mean, the targets here, I don't remember what the targets are offhand, but 3 kilometer grid spacing is the coarsest one that we're talking about, and then 1 kilometer for nests. And maybe Vijay would be so kind as to respond to that in the chat with more specific information. But yes, we're already doing that. That's already part of the project.
Okay. Next one is more of a statement from Matthew Rosenkrantz. He says, climate testbed will be very interesting, very in all caps.
Very interested, I suppose.
Oh yeah, very interested, sorry.
Yeah, okay, great.
Yeah.
You know, we would definitely need to have some input from the climate testbed and work with them, absolutely.
Okay. And the last one is from Jeff Whitaker. He asks, regarding international partnership, the UK Met Office is contributing to the JEDI development. JEDI is the data assimilation component of the UFS.
Yeah, he's just correcting what I said earlier, so thanks, Jeff.
Yeah. And Vijay again is adding on to a previous question. He says, short range weather app, standalone regional model will have the capability to set up regional grids with different sizes and configurations.
Yep.
Yeah. So looks like that's all the questions we have for now.
Great. Well, thank you very much. I'll give up the show here.
All right. Thank you all for attending the webinar. I'm happy to give you back 7 minutes from this meeting and hope you have a nice rest of the evening. Thank you.
Thank you.